and I will be the presenter today for this webinar, Ethical Issues from the Tacoma Narrows Bridge Collapse. If I assume that you can all hear me, and if you can't, let me know. Let's see, I'm trying to find my controls here, questions and answers, etc., etc. Okay, ethical issues from the Tacoma Narrows Bridge collapse. The way the webinars move forward here is I press on with the presentation for 50 minutes, then take a 10-minute break, come back, do another 50 minutes, 10 minutes, 50 minutes, 10 minutes. Now this is just a 2 PDH or 2-hour webinar, so we'll only go through that cycle twice. And the PowerPoints that we'll be looking at today you may be interested in getting a copy of them for your future interest. And I'm pretty sure you can do that by going to the PDH source website, logging into your account, following the instructions, and you should be able to download a copy of the PowerPoints. Okay, learning objectives, all very interesting. Okay, now here's kind of what I'll be talking about, the way I'll be slicing up the information today, or the discussion today. I'll talk about the history of the project, how it came into being, and that's important because what happened historically really caused the ethical failure that we'll be focusing on today. And these ethical issues webinars, by the way, there's certainly room for differences of opinion. And there can be those who would have a different opinion of this incident than mine. What you'll obviously be hearing about today is my view of what happened and what the ethical issues were. But if others have a different view, why, that's fine. But the history of the project, I'll be talking a bit about that. The design proposals for the bridge, there were different ones proposed, and then there is the actual design that was implemented. And we're talking about a project in 1940. That construction was completed in 1940. So it's a ways back in history, but it's still quite relevant as far as the ethical issues are concerned. The defect, if you will, that was the prominent defect that was identified was oscillations of the bridge. And we will look at that and see what was done to try and mitigate these oscillations, and that they didn't work, and they led to the failure, the collapse of the bridge. And we'll touch on the mitigation efforts that were made, and then we'll talk about and look at the actual collapse. And one of the aspects of this incident is that everybody knew this bridge was in big trouble, and it was a candidate for a collapse, which of course it did. And this was back in the 1940s, and the when on the particular day of the collapse, the oscillations became quite severe and they closed the bridge to traffic. And people had an opportunity to go out there with their 8mm cameras and film the collapse. And several of these films exist and today, and a few of them are posted on YouTube, and we'll be looking at one of those. So the bridge collapsed. Then there, of course, was a post-mortem, an investigation to determine what the cause of the collapse was. And then we will look at lessons learned. In other words, did the engineering profession, the bridge design profession, learn from this incident? And the answer is yes, and certain significant advances were introduced into the bridge design process as a result of this failure. And then the aftermath of after the bridge had collapsed, after a certain amount of time passed, a replacement bridge was constructed and is there today and serving quite well. So here is kind of a look at where the ethical issues, as I see them, cropped up. The first one has kind of, I put into the basket of the two kinds of knowledge that we as engineers use in what we do: theoretical knowledge and experiential knowledge. The theoretical knowledge is the stuff you got in engineering school: statics, dynamics, hydraulics, so on and so forth. Experiential knowledge, though, is that knowledge which the engineering profession as a whole has acquired over actually centuries, probably, it's fair to say. And in other words, how have things been done in the past? Did they work? And if they did, why we can use that as a basis for a new design that we are working on. What do we do when the experiential knowledge is inadequate? Nobody has built a building, designed and built a building this tall, as tall as the one we want to build, or a bridge with a span as long as the one that we want to build or have to build. And what do we do to supplement the experiential knowledge? And I'll have comments there. Another important point that this incident illuminates is the commercial interests that come into play when you have major engineering projects that are to be undertaken. The pushing and shoving over who is going to get the design contract or the design work, who is going to get the construction work. So commercial interests are very important in this story, I believe. Here, by way of introduction, is a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight-ahead designer, cranking out drawings and specs for the construction of buildings and a fairly broad spectrum of related infrastructure. I'm not a bridge designer, but don't hold that against me, please, because you don't have to be a bridge designer to understand the ethical issues with this project. After that 35-year stint, I had an opportunity to do something that I had always been interested in, which was in the what might be characterized as the public policy arena. And for 9 years, I was a principal advisor to the California legislature, principal staff advisor to the California legislature on infrastructure and capital outlay issues. So that's me. Okay, what are we talking about here? We're talking about the Tacoma Narrows Bridge, and we are talking about the original, the first Tacoma Narrows Bridge. And it is in Washington State, up there in the upper left-hand corner of the 48 United States. And it was constructed to cross what was called a body of water called the Tacoma Narrows, which is part of Puget Sound, crossing from the city of Tacoma to an area on the Olympic Peninsula called the Kitsap Peninsula. And it was the third longest suspension bridge in the world at the time. Construction was completed in July of 1940, and in November of 1940, it collapsed. Now, to get the best picture of what's going on here, this is the location of the Tacoma Narrows, and that's where the Tacoma Narrows Bridge was. You see the city of Seattle up there in the upper right-hand corner. You see Olympia, Washington in kind of the lower left-hand corner. That's the state capital. And then between them there is Tacoma, which I believe is the second largest city in Washington State. And you see the, in this view, this map, if you will, those dark blue areas, that's the Puget Sound, which is the the bay, if you will, serving Seattle, and it leads out into the Pacific Ocean. And the area on the left-hand side here is the Olympic Peninsula, a very large, very sparsely populated, heavily forested area, and a source of a great deal of timber. And the timber industry, of course, has been very important in the history of the development of Washington State, and continues today. Now, you also see on this picture some other places, a place called Fort Lewis, a place called McChord Airfield, and a place called Bremerton Navy Yard. And these are today and were very much back in the 1930s, 1940s, very important strategic military facilities. The Bremerton Navy Shipyard is a very important facility for the U.S. Navy on the Pacific Coast, probably second only to the naval station at San Diego. And the Fort Lewis is an Army base. And then there is McChord Airfield, which initially and back at this time, McChord was an Army airfield. And it, because back at that time in the 1930s, 1940s, there was no Air Force. The airplanes belonged to the Army. So, but after World War II, the Air Force was established, and McChord became McChord Air Force Base. And then in relatively recent years, McChord and Fort Lewis have been administratively joined together in the latest fashion as a joint Air Force Army base. But the reason that the McChord and Fort Lewis were where they are was to a large extent to protect the Bremerton Navy Yard. Um, the uh, uh, there was the military necessity for a bridge at the Tacoma Narrows was to a large extent driven by military concerns. And remember, the time that we're talking about is back in the mid to late 1930s, and there was the looming specter of World War II coming, and one of the major concerns was, as far as the U.S. military and the U.S. federal government was concerned, was the defense of the U.S. In the event of an attack by Japanese. And of course, we all know that that attack did materialize at Pearl Harbor in Hawaii, but there was a very significant concern that an attack would come from Japan at the at Washington State and targeted essentially at the Bremerton Navy Yard, as at in Hawaii it was at Pearl Harbor. And that upper left-hand corner of the United States, the Pacific Northwest, Washington State, that is the part of the 48 United States that is closest to Japan. And so there was very real fear and concern that an attack would come against the United States at the Pacific Northwest, Puget Sound, and the Bremerton Navy Yard. Now, Puget Sound, the bay, if you will, that connects Seattle and Tacoma and so on and so forth to the Pacific Ocean, you'll notice that it's a real can of spaghetti, waterways running all over the place. And these waterways block traffic up in this area. It's quite difficult to get from on the Olympic Peninsula, for example, from one point to another in a straight line because you keep running into these Puget Sound bodies of water. So this is what we're talking about, and the bridge that we were talking about is there at Tacoma. The Tacoma Narrows is the body of water that the bridge was crossing. Just to give you a feel for driving distances up in this area back at that point in time, late 1930s, early 1940s. From the city of Tacoma to a place called Gig Harbor, and I'm not quite sure exactly where that is, but it was somewhere on the Olympic Peninsula. Before a bridge was built at the Tacoma Narrows, that was a 107-mile drive. If you could get a bridge built across the Tacoma Narrows, it would only be 8 miles, and driving time would be reduced from 2 hours and 10 minutes to 17 minutes. Now, in civilian terms, you might say, well, okay, a couple hours, that big deal. You know, you can get stuck in a traffic jam in LA for 2 hours. And so from a civilian perspective, some of these time differences don't sound that important, but from a defense standpoint, they are. They're very important. And this was very much illustrated as an example as a result of the Japanese attack on Pearl Harbor and how quickly it took place, and that the U.S. Did not have time to mount any sort of a defense at Pearl Harbor, and you had great harm done to the Pacific Fleet as a result of that attack. It happened that a number of the major capital ships of the U.S. Navy were at sea when the Japanese attacked at Pearl Harbor, and so they avoided damage. But we all know about the damage and the harm that was done at Pearl Harbor. Okay, from another important point to point is Bremerton Navy Shipyard to McChord Air Base. McChord, a major purpose was to defend Bremerton. Without a bridge across the Tacoma Narrows, that was a 79-mile drive. If you could get a bridge across the Tacoma Narrows, that would be a 39-mile drive, reducing the driving time from an hour and 50 minutes to 55 minutes. And again, that doesn't sound like a lot in civilian terms, but from a military perspective, it was very important. And then some other distances there, Tacoma to a place called Port Orchard, which was on the Olympic Peninsula, 91 miles, reduced to 21 miles if you could get a bridge at the Tacoma Narrows. Tacoma to Bremerton, very important, 90 miles, could be reduced to 30 miles. Driving time reduced from 2 hours to 40 minutes. So important savings in driving time and the ability to move military from Fort Lewis and aircraft from the air base McChord to the defense of Bremerton. Here is an aerial photo today, and the body of water is, of course, the Tacoma Narrows. That's the city of Tacoma on the right, and the bridge that you see across the Tacoma Narrows is the bridge that is there today. On the left-hand side there, I haven't had a chance to verify this, but let's see now. I've got a phone call here, and I need to get rid of that. Okay, that thing you see on the left there, to my eye, looks an awful lot like a World War II era airfield. And so again, if back at that time, 1930s, there was no bridge, and so it would be a long drive winding around to get to that airstrip, if that's in fact what it is. So here we are in the 20th century, and no bridge across the Tacoma Narrows. The let's see. I want to check something here. I'm checking my controls. Stick with me. Uh, okay. So here we are in the 20th century, and actually back in the 19th century, in the 1800s, is when interest began to perk up in the Pacific Northwest about the issue of a potential bridge at the Tacoma Narrows. And back in the 1890s, early part of the 20th century, logging, very important industry in the Pacific Northwest, a lot of timber, very heavily forested. And the sawmills, if you will, the market for timber was south of the Tacoma Narrows in Washington State, and the logging industry. The only way to get the timber out of the Olympic Peninsula was with horse and buggy and wagons, because this, of course, is before the automobile and before the trucks came onto the picture. And even if you did have automobiles or trucks, motorized trucks, you still had a very long, circuitous trip to get timber out of the Olympic Peninsula to the sawmills. So this is back in the late 1800s, and the railroad industry had been established now and was active in the Pacific Northwest. The railroad that kind of had the whip hand in the Pacific Northwest was the Northern Pacific, and it saw the potential for the timber industry on the Olympic Peninsula, and it felt that it had real commercial opportunity to haul this timber out of the Olympic Peninsula uh, if a railroad could get into the Olympic Peninsula, but it was blocked by the Puget Sound waterways, and particularly by the Tacoma Narrows. And so back in the 1880s, the Northern Pacific Railroad began to uh, take an interest in building a bridge across the Tacoma Narrows. And what it wanted to build was a trestle bridge, a low level bridge. And for one reason, it's the cheapest kind of bridge that could have been built. But also, railroad trains don't do well with steep grades. And so a high level bridge would be impractical across the Tacoma Narrows Bridge, or as far as the railroad was concerned. And uh, also about this time in the US, the federal government, and as well as state governments and this sort of thing, uh, were becoming aware that the waterways throughout the United States uh, were an important asset for transportation purposes. The big actor here was, of course, the Mississippi River and all of its tributaries. And if you allowed low-level bridges to be built across these waterways, the Mississippi River and the Tacoma Narrows, you would be blocking river traffic. And so legislation and regulations were enacted that, in essence, said that no navigable waterway can be obstructed, and that includes bridges across navigable waterways. And the Tacoma Narrows is a navigable waterway. And so the idea that the Northern Pacific had to build a low-level trestle bridge ran afoul of this federal legislation and requirements. So that back in the 1880s and the early 1900s put the nail in the coffin, if you will, to the idea of a bridge across the Tacoma Narrows. Also, there was a major concern about the cost of building a bridge. And who was going to pay for it? Pacific Northwest was sparsely populated. The state of Washington didn't have the money. The Northern Pacific Railroad didn't want to spend the money. So cost was a significant concern back at that time. And so we moved through time into the 1920s. And the automobile comes along and trucks come along. And so now there, in theory, is another way to get transportation into the Olympic Peninsula, and that would be trucks that could haul the lumber, haul the timber out of the peninsula to the sawmills. And and then at that time, the Pacific Northwest is beginning to develop with urban centers, Seattle, Tacoma, Olympia, and you get the commercial interests and business interests and local government interests developing. And so you move and you've now got the automobile. And so you're moving into the 1920s, and the business and commercial and governmental interests in the Pacific Northwest begin to take an interest in an automobile bridge that would stimulate the economy overall in a large way in the Pacific Northwest. And so some thought began to be put into what kind of bridge could be built that would not run afoul of the federal government's prohibition on obstructing navigable waterways. So in the late 1920s, 1930s, some concepts began to be drawn up, and here was one of them. It was for a suspension bridge. Again, just in the talking stages. And since it would be a high level suspension bridge, it would not obstruct the navigable waterway. Here is a cantilever bridge that was sketched up by the Tacoma city engineer, high enough to satisfy the navigable needs. But there's still the issue of funding. Who's going to pay for it? The city of Tacoma certainly wasn't going to pay for it. The business and commercial interests there in the Tacoma Olympia area were not didn't have the money to pay for it. The state of Washington didn't have the money to pay for it. And one idea that began to perk up was for a toll bridge. In other words, float bonds and then pay them off with tolls paid by automobiles and trucks that use the bridge. And the problem there was that the traffic that was projected to be crossing the bridge at the Tacoma Narrows was quite small, and a toll bridge just wasn't going to generate enough revenue to pay for the bridge. So a desire for a bridge, but no money. And in addition, at that time, since they couldn't see a way to get a bridge built across the Tacoma Narrows, the state of Washington said, well, let's at least start a ferry service and across the Tacoma Narrows. And so the state of Washington let out a contract, a concession for a ferry operator. So at least people could drive down to the water, get on a ferry, and take it across to the Olympic Peninsula. But that had limited capacity. And of course, it was a very slow way to get across and still would take a lot of time to get from McCord and Fort Lewis to Bremerton. And so the concession contract was let to a private company called the Washington Navigation Company in 1926. And this concession agreement had a no competition clause in it, which seems logical because nobody would uh, incur the cost of running a ferry across the Tacoma Narrows if there was going to be competition. Another ferry service might be started. So this concession agreement said that there will be no competition, no competing ferry service for 10 years until 1936. And this no compete provision also encompassed the construction of a bridge, because of course if a bridge was constructed, then that would be a very serious competitor for any ferry service. So 1926, we've got the automobile, we've got motorized trucks, uh, and all we've got is a ferry service across the Tacoma Narrows. But as we moved into the 1930s, a couple of things happened that substantially improved the funding prospects for a bridge. The first of these two things that happened. Well, first of all, the concession contract expired in 1936, in the middle of the 1930s, and the other thing that happened in the 30s as we moved forward through the 1930s was the specter of World War II on the horizon. The increased threats on the Atlantic side from Germany and Italy, and on the Pacific side from Japan. And so the Department of Defense, it was called the War Department back at that time, began to take quite a bit of interest in a Tacoma Narrows bridge as a way to move defenders from Fort Lewis and McCord to protect Bremerton. So we're moving through the 30s. The the War Department, the Department of Defense, begins to take an active interest in getting a bridge built across the Tacoma Narrows. The other thing that happened in moving through the 1930s is the Depression during the Roosevelt administration. And it started, of course, in 1929 with the collapse of the stock market. and many people were out of work. And the federal government was taking an active interest in pulling the country out of the Depression, putting people back to work. And one of the approaches the federal government was focused on was public works projects, building things like highways and office buildings and bridges and port facilities as a way to put people to work in the construction industry initially, and then provide continuing employment opportunities after this infrastructure got constructed. So the Depression era is begins to be an important factor as far as the Tacoma Narrows Bridge is concerned, because this is exactly the kind of project that the federal government was looking at, was public type projects that would stimulate the economy. So these two factors, the military factor, uh, concern about an attack by Japan in the Pacific Northwest, and then the economic factor, the desire to get people back to work. And these coincided with the fact that the ferry concession agreement expired in 1936. So the funding picture begins to look significantly brighter to get funding for a bridge. And the entity that was being looked at to get this funding, of course, was the federal government. And so the state of Washington, its Department of Highways, undertook to put together a proposal to the federal government for funding for a Tacoma Narrows Bridge. And this effort in the Washington State Department of Highways was under the direction of an engineer named Clark Eldridge. And he and his engineering staff employed in the Washington Department of Highways prepared plans for a suspension bridge that was of conventional design. Now, the key feature of the bridge that is important here is the roadway support girders. And the conventional design practice back at that time, and even continuing today, is to have the roadway support girders be truss girders, open truss girders, and very deep truss girders. Because as you'll recall, when you make the cross section of a girder or a beam deeper, it's stronger. So a 25-foot deep truss girder reflected the state of the art of in-bridge design for suspension bridges back at that point in time. And that's what the Washington Department of Highways proposed to the federal government for funding. And stick with me here just for a minute while I check. Okay. And so now another important aspect of a truss girder is that it is open, and wind can blow through the truss girder without having a whole lot of effect on the roadway support girder, because the horizontal winds blow right through it. And the Tacoma Narrows is a windy place. They get some significant winds there. So the state of Washington took this proposal to the federal entity that controlled the federal purse strings, something called the Public Works Administration, and Washington State requested $11 million for the bridge. Now, remember, we're talking about 1930s era dollars here. So obviously, in terms of today's dollars, it would be much, much, much more. Here's Clark Eldridge, who was leading the effort, the engineering effort for the Washington Department of Highways. A point of interest, it's not relevant at all to what we're talking about here today, but back at that point, in time, the director of the Washington State Highway Department was a gentleman named Lacey Murrow. And Lacey Murrow was the brother of the very well-known Edward R. Murrow, radio and later television newscaster for networks. Just an interesting sidelight there. So here is the design that Clark Eldridge and the Washington State Department of Highways came up with. Suspension bridge, high level, so it's not obstructing the navigable waterway. And the key feature is that it had was 25-foot deep open truss girders supporting the roadway. And this was then and continues to a large degree to today to be the standard operating procedure, well known and significant bridges had been built with this type of roadway support girder successfully. So a conservative conventional design. Now, let's see, I'm checking my clock here. As happens practically almost every time you have a large public works project or undertaking that is in the mill, if you will, there develops a competition between in-house government agency engineers and private engineering firms. The in-house government engineers with the Washington Department of Highways, they wanted to design the project. That's just the way engineers are. They want to, and then private engineering firms wanted to get the contract to design the bridge. And that, of course, is an economic concern interest for the private engineering firms. And so a group of East Coast engineers under the leadership of a gentleman named Leon Moiseev, who I want to tell you right up front, at that point in time was a very well-known, very successful bridge engineer and had a sterling reputation up to that point in time. But one of the ways when you get this competition between government engineers and private engineering firms, one of the ways the competition plays out is on the basis of cost. Each group is saying, I can do it faster, cheaper, you know, so on and so forth. And from the record, Mr. Moiseev came across a theory that had been developed in Austria I believe it was just simply an academician for a different design for the roadway support girders, which are very expensive. And that if the roadway support girders were not constructed as as a truss, but rather as in a solid I-beam configuration, the cost could be reduced. Mr. Moiseev and his engineers said could be reduced from 11 million to $8 million. And again, we're talking about 1930s era money. So this is a lot of money back then. And Mr. Moiseev's group went to the folks there on the East Coast in Washington, D.C., who controlled the purse strings, and said, look, uh, if you we can design this bridge and get it built for only $8 million, we'll save you $3 million, and you'll get the bridge. And the entities at the uh, federal agency that controlled the purse strings, I don't know this is a fact, but I've over the years seen this all the time, is that the folks who control the purse strings are almost never engineers. They are budget analysts or bean counters. And so and I hope I'm not being too harsh here, the bean counters with the Public Works Administration said, oh, well, gee, we can save $3 million if we mandate that the state of Washington farm out the design of the bridge to these East Coast engineers. And that's the way the project moved forward. The federal government said to the state of Washington, we'll give you the money for the bridge, but only if you farm out the design of the bridge to these private engineers on the East Coast. And the Washington state engineers were livid. Clark Eldridge and his engineers, they protested. They said that that Moiseev's plan was fundamentally unsound. Okay, I'm looking at my clock here. We've got about 7 minutes before the hour, and it's time to take our first break. So let's do that now, and then we'll come back and pick up here. And we'll come back at about 5 minutes after the hour. So I'll see you all in about 10 minutes. The bridge is, funding for the bridge is looking quite feasible now because of the military concern and also the economic concern, the desire to pull the country out of the depression, and the competition, of course, pops up between the in-house government engineers with the state of Washington, the and private engineers. And the group of private engineers led by Mr. Moiseev said, we are going to design it cheaper using what was an unproven approach. In other words, the experiential knowledge was not there for this approach to the girders. And the bean counters with the federal agency that controlled the purse strings said, oh, wow, we can save money here, so let's give the state of Washington the money for the bridge, but mandate that they have to farm out the design to Mr. Moiseyev's group. And that's what happened. This is Mr. Moiseyev, and I want to emphasize that Mr. Moiseyev had a sterling reputation as an engineer, as a bridge engineer, up until this point in time. But he, in order to compete for the project, elected to propose an unproven approach to the design. And here's a picture of Mr. Moiseyev's design. You see the shallow I-beam girders, only 8 feet deep, as compared to the 25-foot deep girders in the Clark Eldridge's design. And the solid I-beam girders are solid, and so the wind, the horizontal winds, do not pass through the girders, but impact the girders. Let's see, there's a chart I'm looking for. Another factor that came into play here is the fact that the roadway was narrow. It was only a 2-lane highway across the proposed bridge because it was the amount of traffic was projected to be light. And when you reduce the roadway width, that makes the girders even less stable. And so that was another consideration. Now, here's a table that I think illustrates what we're talking about pretty well. Compares 4 suspension bridges. The George Washington, which is back on the East Coast. The center span was 3,500 feet. The girder depth was 36 feet, very deep, very strong. The width of the roadway was 106 feet, and that was probably a 6-lane highway. And so the very deep girders, very wide flanges, if you will, and so you had a very rugged bridge completed in 1935. Key ratios to get the picture here. At the George Washington, the ratio of the girder depth to the length of the center span was 1 to 120. The ratio of the width of the roadway to the length of the center span, 1 to 33. The Golden Gate, which is in Northern California where I am, completed in 1937. The girder depth was conventional open girders, 25-foot deep, roadway width 90 feet. The ratio of girder depth to length of center span 1 to 168. The ratio of the width to the length of the center span 1 to 47. The Bronx Whitestone on the East Coast, and the Bronx Whitestone was essentially, as I view it, the evil twin of the Tacoma Narrows Bridge. It the same philosophy, design philosophy that was used at Tacoma Narrows was used at the Bronx Whitestone. And the configuration of the Bronx Whitestone is very similar to that of the Tacoma Narrows. And the Bronx Whitestone, which was completed just about the same time as the Tacoma Narrows, immediately began to experience the same issues, oscillations that the Tacoma Narrows did. The Bronx Whitestone, uh, the managers of that bridge had the benefit, if you will, of observing the Tacoma Narrows failure, and they immediately began a program of remedial measures to strengthen the Bronx Whitestone. And they got the remedial measures in place in time. And the Bronx Whitestone is now, did not fail, it did not collapse, and is there today uh, uh, doing a good job of carrying its traffic. So the Bronx Whitestone, the girder depth was only 11 feet, very shallow, much shallower than at the George Washington or the Golden Gate. The ratio of the girder depth to length of center span, 201 to 201, still higher than the Golden Gate and the George Washington, but not grotesquely higher. And the ratio of the width of the roadway to the length of the center span, 1 to 31, the same vicinity as the Washington and the Golden Gate. And then you see the Tacoma Narrows, the girder depth was only 8 feet, less than a fourth of that at the George Washington. And the girder was a solid I-beam configuration, not a truss configuration. So the wind did not blow through the Tacoma Narrows girders. The width of the roadway, only 39 feet. And these key ratios as far as ruggedness and strength is concerned, the ratio of the girder depth to the length of the center span at Tacoma Narrows, 1 to 350, compared to George Washington, 1 to 120, Golden Gate, 1 to 168. And the ratio of the width of the roadway to the length of the center span, 1 to 72, compared to 1 to 33 at George Washington and 1 to 31 at Bronx Whitestone. So that, though, is the design that the federal government said they would fund, and the state of Washington Department of Highways reluctantly acquiesced because that was the only way they were going to get the money for the bridge. So construction of the bridge began in September of 1938. The bridge was completed and open to traffic in July of 1940. Here are some pictures of the bridge under construction. The bridge begins to take shape, and you can see that it's a very elegant bridge that is being built. Here's the bridge completed. Again, very elegant, light, and very beautiful. Another picture, and you see the roadway support girders, solid I-beams, and again, they were, as a result of being solid webs, they seriously impeded the flow of the horizontal winds through the Tacoma Narrows. And again, winds are a significant consideration at the Tacoma Narrows. Here's the guys that were doing the heavy lifting, opening day. And here is the opening ceremonies, first traffic coming across the bridge. You see it is a narrow 2-lane roadway. And the commemorative program for the opening of the bridge in July of 1940. And even before the bridge was completed, the people working on the bridge began to experience serious oscillations. And the bridge became, well, even while still under construction, uh, became known as Galloping Gertie because of the up and down transverse oscillations that were being experienced during construction. And the bridge opened on July 1st of 1940. It became something of a tourist attraction. People from Seattle on a Sunday afternoon would go out for a drive in their cars and specifically drive across the Tacoma Narrows Bridge and experience the kind of wild ride that was there as a result of these oscillations. And the bridge managers, the state of Washington, had a problem with this bridge. They retained the services of a Professor Farquharson at the University of Washington to review the design, to investigate, and to develop mitigation measures that could control or eliminate the oscillations. Here is the state of the technology that Professor Farquharson had available to him. Um, an 8mm movie camera and a level. And here are his notes from his field investigations. Some Band-Aid type mitigation measures were attempted and did get in place before the bridge collapsed. Tie-down cables were put in place. Hydraulic buffers were installed between the towers and the floor system of the deck to damp the oscillations, but neither was effective. And one of the more bizarre proposals was to drill holes in the solid girders so that the air would pass through them and not act as aggressively on the girders. This idea needs to be cooked a little more because obviously if you're drilling big holes in the flanges in the web, you're going to weaken the girder. So that was not a real swift idea. Another idea that was identified was to provide some streamlining around the girders, and that had some value. And here, for example, you can see a picture of the Bronx Whitestone Bridge and the remedial measures that were put in place on it because the managers of the Bronx Whitestone were made aware of the weaknesses they had as a result of the experience that the Tacoma Narrows had. So the girders were stiffened by the addition of trusses. This was in 1946. And then streamlining around the solid girders was put in place in 2004. Now, this incident that took place, the collapse took place in 1940. And you might be thinking, well, geez, why did it take them until 1946 to get any remedial measures in place? Well, the reason is that during World War II, there was a great shortage on the availability of steel, and the materials were not available to for this type of project. All of the country's steelmaking capacity was devoted to the war effort. And so bridge opens in July of 1940. On November 7th. The wind was blowing through the Narrows at a steady speed of about 42 miles an hour. Stiff wind, but steady. And that's important, and we'll see why. And at 10 a.m., the bridge began to oscillate severely in the torsional mode, and the bridge was closed to traffic. The bridge had been oscillating since it was under construction in the transverse mode, up and down, up and down, up and down. And on this day, it began to oscillate in the torsional mode, clockwise, counterclockwise, clockwise, counterclockwise. Probably this was due to suspender cables finally breaking on one side, and that altered the support of the roadway asymmetrically, and the bridge began to oscillate in this torsional mode. This at 10 a.m. on November 7th, the torsional oscillations are observed, the bridge is closed, and at 10 a.m., the center span collapsed. And here are some photos, and uh, and here you can see the torsional twisting of the bridge. The sidewalk on one side was 28 feet higher than the sidewalk on the other side. And here is the actual collapse. Remember that everybody knew this bridge was going to collapse, and so there was an opportunity for people to film the collapse and to take still photos of the collapse. Here is another picture of the debris. Another picture. Damage to the cables. And there was some twisting and buckling of the towers. Now, as I indicated, there are some videos. These were taken from the 8mm movies that were filmed that are available on YouTube, and you can review these at your leisure. Now, though, we're going to see a video here, one of them. And this is about a 5-minute video. Okay, so that was the collapse. And because there was ample advance warning, the bridge was closed, traffic was stopped, and there were no fatalities, with the exception of a small dog who was in that car that got trapped on the bridge. So that's fortunate that there were no fatalities. Um, so the incident takes place. There, of course, is an undertaking to investigate the collapse and try to determine what the cause of it was. It was under the direction of an entity called the Federal Works Agency. It looked at random fluctuations in velocity and direction of the wind, perhaps as um, a cause, fluctuating eddy currents, the von Karman effect could have been a factor, and then resonance or self-induced vibrations caused by wind fluctuation. Now, the resonance theory really didn't pan out very well for the simple reason that the wind speed, although high, was constant, and to have resonance uh, as a consideration, you need to have uh, a vibrating or alternating forcing frequency. The wind would have to be vibrating, if you will, fast, slow. And that was not the case. So resonance was ultimately ruled out. Um, the uh, the investigation focused on uh, the fact that this was the first suspension bridge to use solid I-beams to support the roadway. And the torsional vibration mode, clockwise, counterclockwise, that uh, the speculation was, and it seems pretty um, reasonable, that all of the transverse vibration that had been going on for some period of time had resulted in one or more of the suspender cables breaking, which resulted in an asymmetric support for the roadway. And as a result, you got the torsional vibration mode. The resonance hypothesis. This is a little bit of discussion on these slides of the resonance theory, and you're welcome to review it at your leisure. But like I say, it seems to be pretty well understood today that resonance was not the cause of the failure. The von Karman effect, and Theodore von Karman who was a very well-known aerodynamicist at Caltech, and he postulated and illustrated the von Karman effect. In other words, when you put a blunt body in an airstream, the air tends to spin off of the backside in an alternating fashion. So you have, and this was originally developed in the field of aircraft design. The wing foils in the airstream would spin off in an alternating fashion and cause vibrations. And the same thing occurs when you put a blunt body like a bridge girder in an airstream. So flutter, aeroelastic flutter probably was an important uh, phenomena in the what happened. The aeroelastic flutter, a way to visualize that is if you take a piece of paper, a strip of paper, say uh, 1 inch wide by 11 inches long, hold it out at arm's length in front of you and drop it, and it passes through the airstream falling to the floor, and it flutters. And so that aeroelastic flutter was probably a consideration in the behavior of the bridge. So you had the bridge deck that was subjected to a horizontal wind, and alternately, without getting into a bunch of details, it causes the bridge deck to twist, and that was observed. So aeroelastic flutter is probably a pretty good uh, candidate for the phenomena that was uh, acting on the bridge. Another very distinguished bridge engineer was on the review panel, Othmar Amon, and he wrote that the Tacoma Narrows Bridge failure has given us invaluable information. It has shown that every new structure that projects into new fields of magnitude involves new problems for the solution of which neither theory nor practical experience furnish an adequate guide. It is then we must rely largely on judgment, and if, as a result, errors or failures occur, we must accept them as a price for human progress. Now, I don't really quite go along with that. The business about just relying on our engineering judgment, and if it fails, that's just the price we pay. I don't go along with that, because I think there is a methodology for how to approach engineering challenges when you are stepping outside of the experiential envelope. In other words, there has never been a bridge with this configuration designed and built in the past, so we don't have any experience. And I think that there are ways, and I'll touch on these shortly. Um, so just to cavalierly say that, well, if we step outside the experiential envelope and the bridge falls down, well, that's just the price we have to pay. I don't really go along with that. So it kind of, in a way, one of the ethical issues here is the conflict between, or not the conflict, but the concept of there being theoretical knowledge and experiential knowledge. Theoretical, again, the stuff you learned in engineering school, F equals ma, hydraulics, statics, strength of materials, so on and so forth. But the other kind of knowledge is experiential knowledge. How was this done in the past? Did it work? Can we benefit from that knowledge? And what happens if we, because of the engineering challenge we need to step outside the experiential envelope. In other words, design a bridge where the longest suspension span was 3,000 feet. We need to go to 3,100 feet or 3,200, 3,300, this sort of thing. Well, essentially, I think a couple of the major approaches. First of all, there is modeling. And Farquharson at the University of Washington was planning to conduct wind tunnel tests of the bridge. He didn't have time to do it before the bridge collapsed. Subsequently, he did conduct wind tunnel tests. So modeling of a structure or whatever it is, and seeing if the model stands up. And as long as your Reynolds numbers are right, you can have some confidence that if the if the model did not collapse, then probably the real thing won't collapse. And in this day and age, Computer modeling, of course, numerical methods, has enormous capabilities. And so if you have to step outside the experiential envelope, one tool that you have available to you, an ethical tool, is modeling. The other ethical tool that you have available to you, or another one, in my view, is redundancy. In other words, um, the a structure of this type um, has never had more than so many suspender cables in it. Let's throw in a few extras just to be safe. Redundancy. Redundancy is what you do when you're not really sure what you're doing, and you just throw in some additional strength or whatever as appropriate. So theoretical and experiential knowledge. If you are the first ethical issue, in my view, is that if you are stepping outside of the experiential envelope, then you need to do so in a rational manner, using perhaps modeling, perhaps redundancy, and there may be things that we could speculate on. And in truth and in fact, this is exactly what happened with the business of bridge design as a result of the Tacoma Narrows bridge failure. Is that now with substantive bridges that are designed, the practice is to subject them to model tests, perhaps wind tunnel tests, or perhaps using computer generated models. But we did learn, the profession did learn from this incident that um, if you that modeling is an important tool that engineers have available to them. Uh, Now, hang on just a sec. Okay, and okay, and then the other ethical issue, in my view, is the economic pressures one. The In this incident, and in many that we encountered in our business, the pushing and shoving between government agency engineers and private engineering firms to get the design work, the design contract. And um, I think that the the issue is simply that do not compete for engineering work by going to the owner, whoever is controlling the purse strings, and saying, oh yes, we private engineers can design this bridge faster, cheaper, better, et cetera, because you cannot. Now, in this case, the reason that you could not make that Moiseyev's team could not make this kind of a statement is that uh, the theory that was developed by this Austrian gentleman was unproven. There was no experience with it, and the uh, in the and there are similar problems with engineers uh, if they try to uh, compete for engineering work by saying to the owner, uh, we can do it faster, cheaper, better, etc. The reason is that on any substantive engineering project, you do not have control over all of the actors and processes and things that need to be done to get a substantive engineering project designed and constructed. You do not, you may think that you're the engineer in charge, or the chief structural engineer, or something like that. You may think that you control all of these different forces, but you do not. Um, and there are, in any engineering project of any substance, there are so many actors involved, and they all have different skill levels, and different economic objectives, and there are just too many forces that at play there, and you cannot say that you can do it faster, cheaper, better, because you can't control everything that goes on in the design and construction process. To try to address that issue, in my view, and this is another webinar, what you need to do is you need to have an organizational structure and processes in place in the design and construction process that force as many sets of eyes to uh, look at and at least put some thought into all of the appropriate documentation on a project. Because even uh, a mechanical engineer could look at a bridge design like this one and say, well, gee, there's going to be a lot of resistance to the passage of the horizontal winds through this bridge. So, in my view, these are the two ethical issues. Is um, if you're stepping outside the experiential envelope, you need to do so in a very reasoned manner, using modeling or redundancy, uh, different things like that. Uh, and because the theory so often is just so crude that it's not going to deal with real situations. And the second ethical issue, in my view, is the one of competing for engineering work, uh, uh, because of the economic pressures that you are faced with. And when this bridge failed, the uh, here's a picture of the Bronx Whitestone again, showing the stiffening trusses. You can look at that as uh, uh, well, it was very similar to the Tacoma Narrows when, and using modeling, and Clark, or Professor Farquharson at the University of Washington was just beginning to put together a program for wind tunnel tests for the bridge, and didn't have an opportunity to do it. But wind tunnel testing now is very common with major bridge structures, as well as computer modeling. And so here, as an example, is a bridge that's near me in Northern California. And there are actually three bridges here, and the latest one is the suspension bridge you see there, and it was wind tunnel tested. It does have solid I-beam support girders for the roadway, but they were wind tunnel tested. And this is how I would summarize the ethical issues. If the theoretical knowledge base underlying a design is weak or incomplete, it must be supplemented by an adequate base of experiential knowledge. Has one of these things been built before, and did it stand up? If the experiential knowledge base is weak or incomplete, it must be expanded until it is adequate. And a principal way of practicably doing this is through appropriate modeling. And the second, in my view, major ethical issue that arises here is don't compete for engineering contracts by telling an owner you can do it faster, cheaper, better. And because you do not control all of the actors in a major engineering project. So that gets us kind of to the end of the story. Clark Eldridge and the Washington State engineers did not take this lightly. They're quoted in the record, U.S. moneylenders blamed by engineers for span crash. The men who held the purse strings were the whip crackers on the entire project. We had a tried and true conventional bridge design. We were told we couldn't have the necessary money without using plans furnished by an Eastern firm of engineers chosen by the moneylenders. And the kind of interesting post-mortem type thing point is that the state of Washington had a number of insurance policies that it had taken out on the bridge, and with a number of different insurance companies and insurance agents. And one of the insurance agents on one of these insurance policies embezzled the money that the state of Washington has paid and did not pass the money on to the insurance company. So the state of Washington took it in the shorts as far as that particular insurance policy was concerned. But most of the cost of the damage was borne by the insurance companies, which is frequently the way it works. And a replacement bridge has been constructed. This is it. Didn't open until 1950. Again, the delays caused by shortages of steel during World War II. And this replacement bridge, you see, has the conventional deep truss type girders supporting the roadway. And another view of the bridge today. And you also see that it's a 4-lane roadway so that that provides additional stiffness for the bridge. And that gets us to the end of the presentation today. And I hope that you've found this to be a little bit interesting and gives you something to think about, and in particular may kind of influence the way you approach projects that come across your desk in the future. So with that, I'm just going to thank you very much for letting me chat with you today. And now I'm going to close things out. So have a nice rest of the day. Thanks a lot. Bye.